recording. Good. Today we're going to talk about assignment number 2. On seminar number 2. Assignment number 1 we just said is okay. Technical there was also not much. So last time, in the last lecture, we talked about the entire workflow, step by step. The lecture was pretty soon up, so I hope at least the ones who were not there were able maybe to look at it. There's a lot of theory in there, which will be useful for this assignment, definitely, because some errors and so on are in there, which are implemented. So assignment number 2, based on the design workflow. Oh my God, is this small? I don't need this. And we need. Can I? No. Can I make this? Yes. So the goal of this assignment is to guide you through the design workflow. Who of you, just that I know also, who of you has done the Vivado design workflow before here on another course? Okay. Okay. Okay, that's fine. Just that I know where to start and on which level we are. That's totally fine. That's what we're doing. That's why we have this exact assignment. So the goal is to introduce the workflow, understand the different steps, understand synthesis, implementation, and simulation responses. So in the lecture, there was described what each of them does. Now we want to see in real life what the tool will give us in response. Of course, the warning messages and what we get as a response is different between each vendor, but there is a general tendency what you do about each of the steps and what these error messages and whatever mean. Of course, we cannot cover all of them, but you get a gist where to look and how to approach them, hopefully. And throughout the course, we will have those appearing here and there. Might seed them into an assignment, make it like an extra small task for you that you learn these things a bit more, because you will code less, but we still want you to be able to fix the things when anything would come if you do your own project throughout the course. We will come to separate projects in the end of the assignment. Yes, and the other part is the responses of the simulations and so on, and then the other part is adapted, of course, accordingly, and then the reporting of your design. So you have different, from the lecture, you know that there's different steps which give you different responses, like resource utilization, power, timing, and those kind of things. Many of them we will cover in much, much more detail later, but this is to make you familiar with the tool, where it is, what it does, how it looks. And for this, you don't have this assignment yet. It will be uploaded after the lecture. You will get 5 files, which basically is a small UART project, which you could try to run on hardware if you want the boards. You could also put a LED blinking to it when you get something, and that's separate projects, which we can talk about in the end. But the goal of this course is also to show you don't need any of the hardware to make your design. Even if you would work with a system on chip, I talked with Kirill about it, the thing is that you could even have emulators. And then you don't even need a processor or doing an operating system that will, ideally, if needed, emulate the entire Linux for you in the simulator. So you can do whatever you want in there, that's fine. So can we do everything with software? That's why we're going to stick to this. You have 5 files. This should enable you to fulfill the tasks. And I will not go into that because I forgot to delete that actually now. Here. The tasks are here. Design entry, as discussed in the lecture. So you load all the files in there, you see how it goes. You have a project coming out. I will also, after I've shown you the task, I will show you in Vivado how the different sections look a bit, that you know something, what are the files for, how do they relate to each other. So maybe there's a hierarchy, maybe you need the one file for something else. What does the design do? I mean, maybe we can just read it from the file name as well, because it is really needed to have descriptive names, descriptive variable names. That's very common. Without this, you will be a bit lost. We will also come actually very briefly coding standards. I can add that as an appendix to the assignment actually, which might help you. Simulation comes after the design entry, as discussed in the workflow. The point is that basically you have your files in there, and the first thing you do after you don't have any syntax error, which the tool will show you, you would go into the simulation. And you don't do any other of the other steps, so simulation is the second task. There is the goal to go towards, and we will look at this also in the seminar, into waveform interpretation. What do the different colors mean? Where do they come from? Why do they exist? And what do we do about each of the colors? How do we resolve these issues? And then basically waveform interpretation and then resolving whatever the waveform shows us as errors. And this will require you to look a bit into the code, a bit understand, but also you have for this 3 weeks time for this assignment. I would take a look at it. Technically, you can do it in a quite short amount, but it really depends how much you have read the code before and how much you can follow now also. I will not tell you everything in the seminar, but there will be useful hints in here. Yes, always important is, I mean, these are like I gave you even what is wrong in a way where you roughly can find it, but the important is, for example, what are you trying to do? What are you simulating and what do you get as a response? And where could this come from? And then you trace the signals. I will show you that in a second. And then we have 2 more tasks. Hello? Did it not compile? Yes. That's interesting. Did it not come? Ah, because we were offline. Of course. Ah. No way.
Yes.
We have to add here task 3 and task 3. Oops, 4. And task 5 we don't really need right now. And this should then, yay, there we are. Can we make this bigger now? No. Sure. There we go. Good. Then after the simulation comes also the synthesis, where there's also, again, actually, I give you the hint, there's a warning in there. In this is a bit more abstract written. I want you that you look through those messages. Without, I will show you this just to comfort you a bit. There's a lot of messages you can get around. I will show you how to filter them. And there's a lot of messages around, but I want you to look at the synthesis messages, warning info, whatever else you might get. And there is one which is particularly interesting, and this will lead actually for you to the code in corner scenarios not work functionally. And this will also answer one of the questions which we had in the lecture about the range of the values, of integer values, because you can custom define that. And yes, and then what should you do about it, and how do you do that? And then there is, of course, out of the synthesis, there comes a report. And because we are always talking about report is resource utilization, power summary, and timing summary. I will show you where they are. And then you can put just the screenshots in here for now, which will then be useful for task 4. Again, look through the messages for implementation step. Look through the messages, anything interesting, anything which is important to know. And then the important part of this part is section 2 and 3, where you go into reporting what of this. So same as a synthesis, so we want to know the resource utilization, the power, and the timing. And then the goal is to report the interpretation. So to compare the synthesis to the implementation, there will be differences. So because you do have much more detail in the implementation and in the synthesis, where do they come from? What are these differences? Think about what they mean. And then there's not written right now here. There is, of course, because there's a lot of time now, and we give you the chance to come up with whatever small project you want to code on top of that. I will give you throughout the seminar now some ideas, and you can code that voluntarily. There will not be not any points or anything, but it's your chance to practice some VHDL or whatever. Any questions on this overview for now? And I will go into the different sections in a second. Each of the tasks will give you 1 point. So I've not written this here, just notice.
What is the actual problem we are implementing? Or
Hey. I will say probably in a second, but technically that's one of the tasks you have to do. What is it supposed to be? Where are we? There's Vivado. So I mean, if you look here at the top file, I don't know. Maybe this helps you.
Can we upload those files to Moodle?
They will be uploaded, just not right now. Although you could have access if you want in between. In GitLab it is, all of it. So also there will be, I forgot one file is in there. There's a git ignore file in there for anyone who wants to work with Git.
Yes, please.
It's not extensive, this one will grow over time, but this might be useful so you can try out different options and you don't mess up your code. Because we are at this part, there is, do I have, yep. We have here, of course, this is a lot of files. You can go into VS Code. I have not done this myself with the command line. You can. This again is an option which you can do. When you code externally, there will be, just as an example, I will go into UART simple, whatever. I write something here, right? And I save it. And then Vivado will tell me I need to reload. So keep that in mind that you're working with two different softwares that you need to cross-reference. So that's a general, no. There we go. Yep. And I can revert this, yes.
So
good.
A little bit.
Good. So that's an overall part. In Vivado, you can also just load this. So basically, you can just go here, and when you open Vivado, you have a project, or you make a new project, and then you load the files in there. I will not do that right now, so that's for your assignment. But you just load the files, and you need to select the correct file in the correct part of the design entry. I've shown this in the last seminar, which sections there are, and then you need to select also the correct device. For the workflow, because I've been working in here before. Exactly. Can we reload this? So, important for, and I'm going to sit down now for this. Ooh. There are a few sections which are going to be really interesting for you for this assignment, or will answer anything you need to do. An overview of your project you find in the sources. The sources have automatically a hierarchy. So this will, a hierarchy. You will immediately know how these files are related, where they're being used. And one thing, just besides Vivado, normal VHDL code, which is also good to know, we're working here already with components. You can look how the syntax for that is. Maybe you can understand already. That will come in the next assignment, how to use components and how to make the things a bit more modular. But it's almost impossible to do a nice project without components. So we have a UART, obviously, in this case. And we have a UARTX and RX entity, which basically one of them is able to recognize a UART stream incoming, a byte, and will put that into a data. Right, so in the RX data, and this will be given out. And on the other hand, we have a UARTX, which will basically take data in and has in related commands like load in. So if you enable load, it will load that data into the internal buffers of that entity. And then there is the UART simple, which is a very simple loop. It will literally just feed back out what you gave it in, and that's when it's going to be the starting project. The goal of this course is also to build incrementally, at least for the workflow, until we get to HLS, maybe before we switch a bit. But until there, we will build on this. And maybe we can do a small project where you send from your computer some data in through UART, you do something with it, whatever, and then you send the result back. This will be like a goal towards what we are. What we do in there, if that's a data router, if we do encryption or whatever, that's we can see. This might also just depend on your HLS project in the end you do. So this is the vision for the different parts. There will be side assignments, because what I can do is I can very easily, and this will cover next time though, just as a kind of small spoiler, I can do many, sorry, not components. I can make many of these components and can reproduce them. And I can every time use this UART entity and reproduce it 100 times. So I can technically, on my FPGA, I can put as many UART ports, RxTs depending, as I have pins on the outside available. So this is something which we will explore. And what is the next time? So this is overall. Also interesting is probably, oops, no, that's the wrong one. Here. So this is how your result will look. But it will look a bit different potentially for you. So you still have to submit it. We have a small coding standard. I will probably put it as an appendix to assignment. It might help you. You can come up with your own coding standard. But for us, when I write a code, I will try to stick to that. And basically, oh my God, this is because of this. There we go. Entities, so that's the high level, that's the block always which we have. They always written in uppercase. And like in general like this, and then a main underscore is between each of the words. If it's a test bench, it comes a small test bench before. We'll show that in a second. Architectures are usually named behaviorals. Vivado automatically generates them as RTL. I don't really care that much about the name, but you might want to have it consistent because at some point you're going to ask, why is this architecture having a different name? For components, you give them usually the entity name plus a number, because I can have multiple components of that entity. And so I can have 10 UART RX, and then I give them a number after that. So it will be, is it from the other project? But that's fine. I can change that to UART if needed. The ports, that's the important part. If you go, important resource actually, for example, NAND. This code is inspired by that, a bit adapted there. They have a different coding standard, so you can always look around. So if you need to FBHDL tutorials or so, you go to NAND. It's probably one of the best resources for that. And you can follow this. And then you have for ports, so the interfaces from an entity outside to the rest of the entity or rest of the design. You have 3 options, in, out, and you have buffer. Although I tend to use in all the designs almost always in and out only, because this will make your design so much easier and you have not any complications with in, out, and Ws and constraints of that. And that's also not where my experience and expertise runs out, because if you avoid the problem in the first place, you don't have to know the corner cases that much. There's something where you can go into Reddit posts or whatever posts and forums and really dive into this, where people have discussions about philosophies about this. But essentially stick to in and out, because you only have inputs and outputs logically. Anything can be a vectors whatsoever. And this comes then in as a so-called suffix, so it comes after your variable name. So it comes to SPI, meso out, or UART RX out, when, for example, the data. Signals can be next negated and will be indicated with an S in the front. Constant and variables have the same, but they have, for constant it doesn't apply with a negated part and next, but they will be basically before. So you always see immediately when you have your code, you know immediately, because you have a suffix, if it's a port, you will immediately know if it's a signal, variable, or constant, and then you already know on which level you're working at. That's why I've been sticking to this coding standard for a while. It's not extensive, but it's simple. And usually I separate different words then by underscore or different parts, like SPI and then meso, MOSI, or UART and RX and TX and so on. The part here, this is up to you. If you learn in this course, we will almost same as we almost don't work with in and out, in outs, and only with in and outs. We also almost will not work with variables. I might cover it at some point short, but there's use cases for this, and you can, if you code the right way with them, then it's fine. But for simplicity, we're going to leave that out, because it will just make it easier, and otherwise you're going to confuse when signals are being assigned, because variables and signals work differently when the value is being taken. And this, of course, then will confuse, because you cannot immediately see that, especially in simulation. And that's something which, for example, I did in my bachelor's thesis. I mixed this up, and then you have a mess. So don't do this in the beginning. I can really tell you. Any questions on that? So this will help you, hopefully, to read the code. We'll upload that to the assignment.
Question about the architectures, like always
Yes.
named behavioral.
Yes.
What's the alternative?
You can name it anything you want. It's just for look. I think you can also make various architectures into one entity, as far as I remember, but it's something which comes less often. So basically, what you do in a VHDL code.
Or what is architecture in this context?
We will come exactly. I will show you in the code. That's why I'm going here. So we have the entity. I think that's so. You have, of course, libraries. You can write your own libraries. And there's always these libraries, IEEE's libraries. You have your entity description, which has your ports. Also, I mean, generics, you can just leave lowercase, very simple, nothing, no suffix, anything. That's why it's not described. Entities are literally values you can give in. So if I want to have a counter, which I give from another entity, I give that a number. I can give that value in. So you have this, and then you make an architecture. And an entity can have multiple architectures. So you give them a name, but usually it's one. It's only one. In many, many cases, there are very few where there's multiple. You can then select between how do I want to have my entity configured. So I implement in an architecture, I implement then all the components, and maybe you want to have the same entity type, but with different amounts of components in there. So I want to have different amount of UARTs in there. And this is basically so I can do an architecture and behavioral, and then you give it a name of UART loop symbol of this entity. But I can make as many as I want again. This is a bit confusing, but just stick to this. For the course, we're going to stick very simple with that. So I partly will try to not confront you with everything. Otherwise, it will become a bit overwhelming. For some of these things, I will just, that's stated, that's how they are. If you want, you can dive into that separately of it, but we're going to keep it simple. And then the rest is, so basically we just have here the UART, the RX, and then the TX, the component. And well, to loop it back, we see if the RX data is ready, so RDY is ready, and then we say load, and if it's not ready, so everything else we set to non-load, otherwise we would constantly load the data in. That's as simple as the loop is. 2 parts here. Actually, one is missing. It's not that important, but we will come later to this when we come to routing and so on. We're working mostly with synchronous clocked processes or any designs, because this will make the routing easier. This will make your design flow easier, so everything is connected to a clock, almost everything. I will come to the exceptions in a second, but they're technically then still connected to a clock. So these are synchronous processes and not arithmetic.
But can you add prescalers, for example?
So that you want a different clock speed, you mean?
Yes.
We will come to that, but not today.
Okay.
There's various options to do that. Yes. And the other part is, sorry, yes, now I have it again, is that you will want also resets. And the resets are important because they will initialize your design. If you don't have a reset, that means you have undefined signals. I mean, how would the design know if I want to be in the beginning high or low? So you make a reset, which will set all the values, and then you can go from there. You may not have to assign to every signal, because then throughout the process, you will only assign the signal when you think your design through after 5 clock cycles. And I don't need it before that, so I will not read it before, so I don't have to reset or assign a value, because it will automatically eventually get a value. We will come to that in timing stuff and the optimizations of design. Just that you know, in general, there's always a reset, but you may not need it for everything because it automatically will be assigned.
Do you mean like a reset procedure, or what do you mean by it?
There's always a reset signal. You have a reset in. When this is high, you assign signals.
Okay.
This is missing in this case, because in this case, I don't really need it.
But won't Vivata complain if you don't connect it up?
If I don't use a signal or a port.
Yes.
I mean, if there's an unused resource, it will give you in a synthesis a warning, yes. So it will tell you, I've removed this because you're not using it. But, you know, like, but again, this goes into compiler-friendly. We had this in the lecture, compiler-friendly, or synthesis-friendly. It's not compiler, synthesis-friendly coding, means that I do not do these things, because otherwise the compiler, the synthese or whatever, or the linter or the implementation has to go through this and recognize all of this. Everything which I remove, which I know I will not use, will make it easier for the tool. Otherwise, the tool has to guess what my intention was. So I will always want to be clear. Same, this is also a user state machine. State machines are generally defined like this. You can look through the code a bit yourself. But you want to always have every state defined. And that's what the compiler will complain about if there is a state not defined. There's not any of the warnings not related exactly to a missing state, but to signals not being assigned in every state. We had this also in a lecture. You want to have in each of the options, you want to have it assigned. And actually the synthesis in this case, as I've put it, does not give you a warning, because it creates an unintended latch or unintended flip-flop in that case. And it will not warn about that, because it assumes that this is wanted. But you will see in the simulation that your simulation will not look as it's supposed to be. So, and you have a lot of files around here, but you see all of them get ignored. They're all grayed out. And what you just need is these 5 files. So VHD is, I think, the entity, like from what it does, how it roughly looks, helps you. I will throw you a bit into the water here so you can dive yourself into there, and then we see how you progress with that. And hopefully we can cover that in between, because when we have to explain and the language and everything in detail, we're not going to get really done, unfortunately. But of course, when there is, for corner scenarios and practical usage where there come limitations, how it behaves, that's what exactly the course is about. Then, test bench. Anyone knows or knows from the lecture or knows themselves what a test bench is for? Yes?
Okay, it wasn't a lecture.
Test the modules to see if they make sense, their input output.
And how does it do that?
Simulating input output.
You simulate, but it stimulates your design. It gives the signals which trigger how design should behave. And this is what we essentially, this is what you always need to understand. You always stimulate the port. So basically whatever port you have, every input port you want to handle essentially. And this is what we do here. Also I left this in here. Vivado will automatically make those kind of headers if you create a file in Vivado. I prefer own headers because they are Doxygen compatible. So for automatic code generation. So I'm just giving you practical use cases for in between. Just a side note here.
But can you in the configuration change the header generation?
That actually, to be honest, don't know, because I've not worked that extensively with Vivado. In my last projects, not.
Okay, but in another tools, have you tried?
There I know that it doesn't work. I would be surprised if Libro can do that, but maybe. It's nothing which we really considered, because we did it later in the workflow when we came up with how we document things and so on. So we started prototyping, and then we changed the headers afterwards.
That's some IDEs, like the support header changes.
That's likely, yes. I just don't know exactly. Here, this is not exactly that important for you to know. We have, besides processes, so processes are just running in a loop every time, constantly, based on how they are being triggered. There's other options. There's functions and procedures as well in VHDL. We are using here a procedure because it's like a function in another method. So we could compare it to that. It's not that, but it does something like this, puts the functionality in a separate block. So I don't have to have everything in the line of code, and the code becomes a bit more readable. We're using here a procedure called send a byte. And this essentially will just for for each time it's being, for E 7 down to 0, so 1 byte, 8 bits, it will just assign the according bit of my byte to the RX. And that's a loop. So that's what it does, just for when you see it. And then we have a unit under test. What is a unit under test? What do we want to test? I can make sure maybe a bit bigger. Oops, no. Help.
Control plus.
Yes, I tried to zoom, but that didn't work. There we are. And I can remove this terminal. There we are. So maybe this is better. What is the unit on the test? So UUT, so either you have DUT or UUT, you have also in a lecture, design on the test or unit on the test. Can be both used. I prefer UUT, that's just a habit. Which one do you think we are testing here? It's written next to it. We want to test the UART loop. So I call this generic here, and that's all I do essentially. And then I need to assign the values and the ports from my design internal. I need to have a clock. And when I start writing it, when I run this, sometimes I forget just because it's one line which appears somewhere. I need to always have a clock in my design, otherwise, because I have a clock-driven design, otherwise I will not stimulate that. I need to have a reset, and which is here missing? Find a mistake. And we have here also send byte, which needs to be assigned to the correct one, which is not the case here.
So you also have to basically provide the data for the testing.
Exactly. There's various ways to do that.
Or you can generate it.
So basically, this is a very, very, very simple test bench. We will have a session on simulation and making this more automatized, because it's a separate real project which you have to do. Because you want to maybe have a configuration file, maybe you have a data file which you read it all out. You want to get automatic messages, automatic responses. This is all not the case. This is just here to get you started and have some as simple as possible. This will look then when we run this. Oh, I closed it. Sad. When I run it, behavior simulation, the lowest level, the rest of them will not be available because you will not have run synthesis or implementation. You cannot run any of them without that. You will see here, and I will cover this because I mean you can Google this as well, but I can also tell you in here. Oops, kind of low. Can I? There we go. Can I make it a bit bigger? View, zoom in. No, thanks. Wow, that's not what I wanted.
They're also next to the button that you just pressed.
That don't make the
No,
UI bigger.
What
in
you?
the toolbar, where the search, save, and then there's loops.
I'm confused.
Yeah, but that won't make the UI. But
Yeah.
just
I think it's fine because you don't need to read the necessary signals. You always have like that's how a simulation looks, very simply put. You have always a clock and always a reset, almost always. So these are clear. If I let it run for a interval of like 10 microseconds as here specified, it will go longer, and it will look something like, can I go here again? Yes. It will just add those to it. I also can run it as long as I want, continuously. And then I will pause it, and that's fine. And then it's even in Vivado, and older tools don't support that. You can put a deep breaking point. So you actually can debug the code like other code, and it will always break at that point, and you can look, how does my simulation look exactly when it comes here? Of course, alternatively, I can also just go here and look for when the signal changes and trace that. So we have running it here for a bit, and I have a lot of data coming on here, and that's what we want to talk a bit about. I want to show you what these different values a bit mean. It's also part of the assignment that you interpret it, and I want that you trace down where this comes from. Can we go here a bit more into the beginning? Will we find this? So, unfortunately, we're missing one color. Oh, I thought a color would be here. Okay. So, there's more than green and red. Green means good, red means bad. Obviously. So green is always the values which are logical, viable values. They don't mean that those are the ones which you expect or anything, but they are stable signals in my design. The X means there's a collision. So I've assigned somehow, if you have seen it maybe, I've assigned a signal to my RX channel. You can ask yourself if that's correct. So this leads to a collision because it's the wrong way around. So I collide one with another. So it will lead to a collision when I put two signals together at the same time. That's also why you don't want to have really in-outs, because it will also give you a warning and so on. In the design, and if you do it in your design, you can technically not do it. It will not compile. But in a test bench, you can drive a wrong signal in a test bench. That's possible. but it will end up in something like this. Then you have here constants. You see this here also. See constant at the UART baud rate, so the interval of the UART, and then we have our constant for the clock period. What we can do now, so we can zoom in and whatsoever, we can also make here certain tags where I can go along, and I can always, you see the clock moving up and down, 0, 1, 0, 1. So I can move and always sample the signals. I can also make multiple of those. I can move them to the next corner, all these kind of things. So you can experiment a bit around with that if you want. What is also nice here, and I've shown this a bit very briefly before, is that you have the option to select different blocks. And this is where it becomes interesting, and that's what you need for debugging, or eventually will need for debugging at some point. Maybe you fix this assignment without it, but it's very powerful that you can just do this. And this will add all the signals which exist in my UART RX0. And if I would have multiple, I will the UART RX0, 1, 2, or whatever, I can also at the same time UART RX2, and I can look at that. And this might not show me the signals right now because I've not simulated them, or not, at least not, they are simulated, but they are not being logged. Just the results of what I see here is being logged. So I can just relaunch simulation, and it will run that automatically, and it will show me then all these signals. And that's where we have my other signal values, which I wanted. And of course I can also separately take then, I can open up a block and then drag a single signal. I don't have to do that block by block. There's also ways that you write scripts for this, which also will help you. Now I will make this small again. Here we go. What is nice here, you can just go through the things, and I will go and, oh yeah, another coding, it's not in coding convention, unfortunately. The TX state will always have like a state, but each of the states is written with a st idle, so st, then so state, idle, start, and whatever, right? But it's always st, so you recognize that immediately when you go through it. Also, a nice thing for your information, I can always make things pink if I want to, whatever. So this might help you if you want to have signals next to it, because this looks a bit blurry, right? In the ideal case, when I'm done with my design, I will have no X's. I might have some red signals, might have some orange one, because they can be undefined. As I said, I might choose that I don't want to assign a reset there, because eventually, throughout my process, it will be assigned. If it's until the end unassigned, there's most likely something undefined, undefined, it will most likely be something like wrong, or I don't touch the signal for whatever reason, I don't reach a state, those kind of things, because logically, I don't want any signal not being defined in any way. Yes, so if you have then everything green, then I would go to making my colors, because it would make it easy to compare. You might also have different stages of like a bus system, so you have it in one part and it reaches later at another part. So I will color them in different parts so I can differentiate between the different signals easier.
Maybe this, so we have logic analyzers and they have fancy input processing. Okay, yep. Basically, for example, I want to, from binary to see the value in ASCII format or something. Yeah.
Where is it? Radix. So I can do binary, hexadecimal, octal, ASCII, unassigned decimal, design decimal, magnitude.
Okay, everything is there.
Yes. Again, if you go, in this every simulation tool, there's not something which should be valid specific everyone, every tool has it somewhere. What I recommend if you go into a bigger project, really make a script which does this. So because right now, I have multiple clocks in here. I have here a clock, and I will have up there a clock, and they're all the same because that's a clock which goes through the design, right? I don't maybe want to have that at 10 times because like it's just going to clog up and make it less overview. So, but then I would need to drag all these different signals or do it manually. So I really recommend make at some point a script which loads all the signals in there automatically, because then every time I run my simulation, that is being called, and I get the simulation immediately in the view, in the section, in the window, in the time frame, with the signals, in the colors, as I need it. So I run simulation, I will see the result, can look at it, can debug again, and run the simulation again. This will really increase your, improve your workflow, but no one told me that really. It's something which is obvious on the one hand side, on the other hand, you might not consider it if you're overwhelmed by everything else. But it makes it so much easier, especially I think as a beginner when you don't know what everything is. These things really help you. Because it costs so much time to just dig through that.
Maybe immediately, how do you save this setup of signals?
In Vivado, so I can save here the waveform configuration. So I can actually, don't even have to write a script in this case. I can just save this right now. I don't know personally how to call it, how to open up the configuration. I've not done it in Vivado. And in models in my Merit, I just, it's
So
very
you
going to
see
be,
the configuration, and when you run it again, you can like open the configuration.
yeah, I will just specify which one it will open here. So this up to you to figure out. I don't expect it for you to do this much now. I dive a bit into it, but in the end, we have a session on simulation and verification, and that's where these automatizations would be covered. I just wanted that this exists for anyone who's really bothered by this. This is not all it can do. So, before people get annoyed. Any questions on the simulation? So this will, and just for reference, if you fix all the bugs, then you have a beautiful, when you start a simulation from scratch without any of the additional stuff, you will have 1 byte coming and in through TX and coming out through RX. That's your goal in the end. And that's also where you should also look at the code again, how this is being done. So, and you see, this is absolutely not what is happening right now. It's just continuing forever. There's a few reasons, step by step, which you can go through. Good. I think this helps here. Now I have to, and of course you can save the configuration and so on. I will not do that right now. Synthesis I can open. It's outdated. We'll see. I will not run it again because hopefully it has this stuff from before I edit the errors again. It always takes a second. It's a very small design, so it shouldn't take for any one of you long. There's a reason why it's that small, easier to understand, faster to run. Any bigger design wouldn't make very, very much sense. And it's also the most tangible. If you would really want to run on a hardware, you would just need like another board which can send you your data in, or a small chip, FPGA chip or something. So synthesis looks like this when you come into it. And what I want you to look first is messages, and they are here. And I have to find the scaling view. Zoom in. No.
Probably somewhere in the settings or something.
Yeah, probably.
Or
These are the functions which you use that rarely. Like when you set it once, you forget about it.
just Control plus.
No, probably not. This is just here on the
Maybe
side.
you want to select.
I'll probably do it here in the text editor. No. Settings. General
Display.
display. Where is it? Ah, there we go. User defined. How big do you want to have it? Something like this? Let's see.
Now it crashes. Yes.
Sorry, I'm sorry, guys.
Let's just continue.
Oh, I have a display loop, no?
It's
Anyways,
Just make a print screen.
Yeah.
Snipping tool and zoom in snipping
Oh,
tool.
magnifier.
Yeah, magnifier as well.
But at least I can kind of.
that's what I meant. There we are. Can I? Ah, there we are. So this should help. Yes, that's all you need to see. Anyways, so right now we have an error. There will be errors potentially in there which I have not yet exactly figured out. Like there's a spawn error, but you don't have to worry about that. So some of the errors are general messages. These are okay. They are related to data, file reloading, any starting, initialization, whatever kind of things related to Vivado itself. You can dig into them and resolve them if you want. Maybe it's also just on my software problem. So what is interesting is we're going to log all this out. So we don't care about Vivado commands. We don't care about general messages of synthesis. We just care about this. And that's what I also mean for your assignments to be relevant. So really the synthesis related of the algorithm when it has run. And you will see here, there's one warning in here after you fix the other errors and warnings in the simulation. This is not something which you necessarily will see in a simulation. Maybe someone discovers it before, or in the code when they go through it, then they might not have it. But essentially, it will be, this will put you here to the counter, and with the counter there's something wrong. And who listened to the lecture will probably know what I implemented here. So this is that. And so basically, I want you to be able to use these tools that you can immediately get into the code and end up there, which is kind of nice. Not every debugger, not every error message, every tool provides you actually with linking directly there. That's a disadvantage compared to when you work outside of Vivado then. It's not all bad. It always depends on your usage. Then we have reports. When I click, I can open all this up. I have a lot of options. We don't care. I gave you the constraints because we will do constraints separately. Set up debug, if you want to play around with it, sure. Open data for, we also don't care that much. We care about report timing summary. Clock networks, you can look around it if you want, that's voluntarily. We care about utilization and we care about power. Schematics you can look into if you want to see how this actually then looks being put into schematic, but I've only looked at that very, very late, or if I need a different perspective. So I will just very simply, for example, say, where's it? Report timing summary. Then I have to, oh my God, that's too big. I just
now disable it.
It's fine. I will, not I have to zoom in and out. No. So I will just default settings. You don't have to do anything. You just click OK. And then you would get a timing report. Very simple summary. We will go in more detail into these. I just want to show you the toolage. And then you get for the synthesis, you would get here a negative slack and various delays, these values. You can look up exactly what they mean. We will come to all that. It's just about the tool right now. Same applies, very simple. Then for utilization, I run here with default settings. I can even export the data if I want to, but we don't need that right now. You can also submit that report to me if you want like this, but I'm fine when you give me a screenshot of this. And for the synthesis part. Because right now you don't, it is just converting into some LUTs, into some registers, whatever, right? And
the Polar Fire, I see they have big Excel sheet for that.
yes. You can get those things very extensively out. It's a very tiny design. You have also here power. That's the prettiest one. We can do also very cool things here. So you actually can give here the output load. You can give the ambient temperature around. You can give the airflow you have around. So really push the limits here, what you can do. And that's what I meant in one of the lectures before, that you can easily give a design. When you have a first design, we have this utilization. That's how big the design is in the worst case. And you can give a design the electrical or the mechanical engineer. For the thermal design, I do this. What is my range, what is my temperature, which I have, and then I get immediately the power utilization. That's a very tiny design. It might take longer with the bigger one, of course. But it will take me how much power it is, how much is dynamic, how much is static, and what temperature I have, how much margin I have to my maximum temperature of the chip, and so on and so on. Again, for you to play around, I care about that you know where you find this and how you use it at this point. And then, so we have these things. That's just that task. It becomes more interesting when we go to implementation. So we'll open the implementation now. We'll take a second. It's also out of date, of course, because of the other errors. I don't want to rerun this, not right now. Generally, you want to, because otherwise you have an outdated design and you're, why do I still have this error? Not because you just didn't run the new one. Will then come here. You have here also design runs. You will have synthesis stage and implementation. This might be a useful point. You see here the difference, that you have different LUT utilization. But of course, you can also go here into reports or open design. Didn't I just? There we are. Wonderful. Report timing? Yes. I can get a timing, and I will have a slightly different timing. There we go. Sorry. I pressed the wrong no button. I was scared that it would rerun. Yes. And there we go. Here again, default settings. and I will get something different. These values you can compare. Ideally, would have like to have a response why it differs between synthesis and implementation. The more precise, the better it will be for you later when you try to make an optimized design. If you understand why the implementation has done this in this scenario, but might be difficult to understand. So that's maybe a bit out of the scope, but as a challenge, you can go towards that. And then, of course, you have the same for the utilization and the power. I don't think there's a point to go into this. And then you have like different reports. I want to see the screenshots of this, the results of this. I want to see in the report of your assignment. And I want that you have noticed the differences which are there and where they come from, why they are there, these kind of things. Yes? And as far as I know, I might be wrong, I don't have any significant warnings in here. Here's a certain visual grid.
What are insignificant warnings?
It's warnings which you cannot do anything about, which are just warning you about something. But that's something which you learn by experience.
Oh.
You also have, for example, this one, parallel synthesis criteria is not met. You Google it in the end, because with these, like how many thousands of different warnings you have. You can Google that, what they mean. In this case, it just means that the design is so small that it didn't require multiple CPU cores. And I would call it an insignificant warning. And of course, you have also a lot of info, which might help you, on the other hand, to like understand what has happened in different steps. Simulation synthesis closed, got license, blah, blah. Let's see if we find anything. Module declared, bound to instance. Now it gives you just information what it does. You can dig into that a bit. No compile time benefit to using incremental synthesis. You know, all this kind of stuff when it does the workflow. That's info. Usually I remove the int, and then there's of course status. So you can get a ton of information, but at least while I work, I untick them because they will be overwhelming. And but they will maybe help you to debug if you have really an issue. Any questions on how to use the tool workflow? And in other tools, you have similar stuff. So this applies, the warning thing applies, and the info applies to other stuff. If you find a warning, it might be useful to dive into the info because there will be more information about your warning. Yes?
We'll probably get questions once we actually
Yep.
to try it out.
Exactly. I think that's okay. What time do we have? I don't have my time today. Okay. Anyways, don't have that much time. We'll probably just, if you don't have any questions so far now, or is any questions on the lecture, anything to discuss? If not, then we can wrap it up a bit, and I will upload it directly now here.
Can we upload it and we have
Yes.
30 minutes to actually try it?
Yes, we can. I think I'm going to stop recording for this now. No. Because it's not needed. Very briefly, there's going to be like an optional task 5, which essentially is about that you can do any kind of code projects in the scope of this UART, a simple extra process or something like this, whatever you want. You have the time now, so it's a perfect chance to do this, so you get a bit more familiar with VHDL before we come back in 3 weeks. So you have the time for that technically. And
what is the time? So we have 3 weeks to assign.
yes. So I mean, I will not get to it, and it's for us. It's always important just that you have the things done before, so we have more of a discussion. Otherwise, we talk about something which you will not understand next time. So if you don't do this assignment, I will base on that next time. I will use the design and make it bigger. So if you, that's the problem with.
If I do the basic thing for the Linux, for the Vivado, and then I want to recreate the same for the Polar file and continue on Polar file, is it gonna be fine?
I mean, for the assignment, for the correcting, the problem is I cannot give you specific errors or warnings, or design flow is going to be different. The more advanced we go, the more the tools will deviate.
Of course.
So that's going to be a problem. So I know that the block design, what we're going to IP cores and all this stuff is next time going to be different.
And understand, but for optional tasks.
For optional tasks, I mean, if you
So I implement the stuff
If-
instead of Vivado, so I don't do the thing twice.
let's put it simply. If you just do like some checksum in here, like we're talking about something small, I cannot read through like 1,000-line code.
Yeah.
If you do like a small, just to practice VHDL, it doesn't matter if you do that in Vivado, so you might as well do it in Vivado. I might just import it over there to Vivado, to have it in this design working. Otherwise, I need to install all the software and everything additional, and I don't have that right now. It's just basically that you it's for you to learn the language, and this doesn't matter in which tool you do that.
No, that's it. Just in parallel, I want to keep two things
Yes.
parallel, so I can switch quickly later.
So I can also.
Other environment.